This lecture is on Chapter 21, the lymphatic and immune systems. Let's start with the lymphatic system. It consists of three parts: vessels, lymph, and organs. The main function of the lymphatic system is to return excess tissue fluid to the blood and to fight disease. There are two general locations: the mucosa-associated lymphoid tissue, also called MALT, and lymphoid organs, except for the thymus. Lymphatic vessels collect lymph from loose connective tissue. The lymph is composed of excess tissue fluid and blood proteins. It carries fluid to the great veins in the neck, and fluid flows only towards the heart. The orders of lymphatic vessels, from smallest to largest, start with the lymphatic capillaries, which are the smallest lymph vessels, then the lymphatic collecting ducts, or vessels, which collect from the lymph capillaries, then lymph nodes, which are scattered along collecting vessels containing white blood cells, the lymph trunks, which collect lymph from collecting vessels, and finally the lymph ducts, which empty into the veins of the neck. So that goes from lymph capillaries to collecting vessels to nodes, trunks, and ducts. Capillaries, collecting vessels, nodes, trunks, and ducts. The lymphatic capillaries are located near the blood capillaries. They receive tissue fluid from the loose connective tissue. The increased volume of tissue fluid causes the many flaps to open and allow fluid to enter. Lymphatic capillaries are highly permeable and allows the entrance of tissue fluid, bacteria, viruses, and cancer cells. Special lymphatic capillaries called lacteals, located in the villi of the small intestines, receive digested fats from the fatty lymph, which is called chyle, and then it can circulate into the body through chyle. This illustration shows the lymphatic capillaries intertwined with the blood capillaries and the many valves that open as the tissue fluid increases. This helps prevent swelling. The lymphatic collecting vessels have the similar anatomy as blood vessels, and they accompany blood vessels. They contain even more valves than veins do, and this helps direct the flow of blood. Lymph is propelled by the bulging of skeletal muscles, the pulsing of nearby arteries, and the tunica media of the lymph vessels, which would be the muscular layer. Lymph nodes cleanse the lymph of pathogens. The human body contains around 500 lymph nodes. Lymph nodes are organized in clusters. You generally don't notice them unless they are swollen as they are engaged in battle against pathogens. This shows a lymph node, and the anatomy includes afferent lymphatic vessels that bring lymph towards the node, and then efferent lymphatic vessels that carry lymph away. And it looks like it's in a hilum here, which is a little divot, like in the kidney bean. This illustration shows the clusters of lymph nodes: the cervical nodes, the tracheobronchial nodes, axillary nodes, aortic nodes, iliac nodes, and inguinal nodes. Lymph trunks are going to occur when lymphatic collecting vessels converge. There are 5 major trunks. There are lumbar trunks, which receive lymph from the lower limbs, the intestinal trunk, which receives chyle from the digestive organs, the bronchomediastinal trunks, which collect lymph from the thoracic viscera, the subclavian trunks, which receive lymph from upper limbs and the thoracic wall, and then jugular trunks, which drain lymph from the head and neck. The largest of the lymphatic vessels are the ducts. There are two major lymphatic ducts, the right lymphatic duct and the thoracic duct. The right lymphatic duct drains the head and neck, the right thorax, and the right upper limb. The thoracic duct drains 75% of the body, basically everything that the right lymphatic duct does not drain. Ducts empty into the venous circulation via the jugular and subclavian veins. Here we can see some of the trunks. There's the thoracic trunk, and then the right trunk, and then also you see the jugular vein, and there's the right lymphatic duct right here, and there's the jugular vein and the subclavian vein. Lymphoid tissue is the most important tissue of the immune system. It has two general locations, the mucosa-associated lymphoid tissue, or MALT, and the lymphoid organs, except for the thymus. For the MALT, it is found in the digestive, urinary, respiratory, and reproductive tracts. Lymphoid organs are designed to gather and destroy infectious microorganisms. There are primary lymphoid organs and secondary lymphoid organs. Primary lymphoid organs include the bone marrow and the thymus. Secondary lymphoid organs include the lymph nodes, the spleen, and the tonsils, aggregated lymphoid nodules, and the appendix. In the thymus, immature lymphocytes develop into T lymphocytes. The thymus secretes thymic hormones and is most active in childhood. The functional tissue of the thymus atrophies with age. The thymus is composed of a cortex and a medulla. The medulla contains Husserl's corpuscles, also known as thymic corpuscles. The thymus differs from other lymphoid organs. It functions strictly in lymphocyte maturation, and it arises from epithelial tissue. This illustration shows the thymus and the medulla and the cortex, along with the thymic corpuscles. The thymus is located in the thorax, like in that mediastinum area. The lymph nodes function to percolate lymph through the sinuses, and most antigenic challenges will occur in the lymph nodes, meaning that pathogens will be fought and destroyed here. And not only are the antigens destroyed, those pathogens, but the B and T lymphocytes will be activated. Antigen presenting challenges are what occur when a B and T lymphocyte are first activated. The spleen is the largest lymphoid organ. It has two main blood cleansing functions: the removal of blood-borne antigens and also the removal and destruction of old or defective blood cells. It is also the site of, or a site of, hematopoiesis in the fetus. For the destruction of antigens, as well as the site of B cell maturation into plasma cells, the phagocytosis of bacteria and worn out RBCs, WBCs, and platelets, also the storage of platelets. There are two types of pulp in the spleen, white pulp and red pulp. White pulp is thick sleeves of lymphoid tissue. Red pulp surrounds the white pulp and is composed of venous sinuses and splenic cords. This illustration shows the spleen, along with the splenic artery and vein, and also a hilum. And you can see the red pulp and the white pulp. Tonsils are the simplest lymphoid organs. There are 4 groups of tonsils: palatine, lingual, pharyngeal, and tubal tonsils. Tonsils are arranged in a ring to to gather and remove pathogens. The underlying lamina propria, or connective tissue, consists of malt. This is an illustration of a tonsil, and these crypts are going to trap bacteria. And sometimes tonsils can get full and tonsillus can form, which are tonsil stones. Let's talk about aggregated lymphoid nodules and the appendix. So malt is abundant in the walls of the intestines that fight invading bacteria and generate a wide variety of memory lymphocytes. Aggregated lymphoid nodules are called Peyer's patches and are located in the distal part of the small intestine. The appendix is a tubular offshoot of the cecum. This illustration shows the aggregated lymphoid nodules within the intestinal wall. And you can see the tiny little cecum remnant, which is our appendix, left over. Animals that need to digest a lot of plant matter will have a larger cecum. Ours is basically vestigial or withered away. So that was the lymphatic system. Now let's talk about the immune system. Immunity is the resistance to disease. The immune system has two intrinsic systems, innate or nonspecific defense systems, and adaptive or specific defense systems. The innate and adaptive systems are deeply intertwined. The innate defense system has two lines of defense, surface barriers and internal defenses. The adaptive defense system attacks particular foreign substances. It takes longer to react than the innate system, and it consists of humoral immunity and cellular immunity. Innate defenses include skin barriers or surface barriers such as the skin and mucous membranes, as well as internal defenses like phagocytes, natural killer cells, the inflammation response, antimicrobial proteins such as interferons and complement, and fever. The adaptive defenses include the humoral immunity, which contains B cells, and the cellular immunity, which contains T cells. We'll start with the innate surface barriers. Few microbes can penetrate intact skin. The physical barrier of the epidermis and the dermis should keep most pathogens out. The skin also releases antimicrobial substances from the sweat glands and the sebaceous glands. It also has an acidic pH, called the acid mantle. Mucous membranes line body openings. They produce mucus and release antimicrobial substances. Various other mechanisms and secretions in different body areas occur in mucous membranes. For example, the respiratory tract contains cilia to help remove trapped microbes. The GI tract utilizes saliva and stomach acid to kill ingested microbes. Innate cellular defenses include phagocytic cells, such as neutrophils, macrophages, and dendritic cells. These cells engulf unwanted substances by phagocytosis. The neutrophils and macrophages destroy engulfed particles. Dendritic cells destroy particles and then present fragments. Antigens are presented on dendritic cell surface to T lymphocytes. This is necessary for initiating adaptive immunity. Macrophages can also perform antigen presentation. This illustration shows the events of phagocytosis. In step 1, a phagocyte adheres to pathogens or debris. In step 2, the phagocyte forms pseudopods that eventually engulf the particles, forming a phagosome. In step 3, the lysosome fuses with the phagocytic vesicle, forming a phagolysosome. In step 4, lysosomal enzymes digest the particles, leaving a residual body. In step 5, exocytosis of the vesicle removes indigestible and residual material. This illustration shows a macrophage in purple using its cytoplasmic extensions to pull spherical bacteria in green towards it. Other innate cellular defenses involve pro-inflammatory chemical secreting cells. Basophils and mast cells promote inflammation. Basophils circulate in the blood. Mast cells reside in connective tissue, mucosa, and internal organs. They release granules containing chemicals. The chemicals increase movement of fluid from blood to injured tissue. They serve as chemotaxis chemicals in that they attract immune cells. Histamine increases vasodilation and capillary permeability. Heparin acts as an anticoagulant. This illustration shows a basophil releasing histamine, heparin, and eicosanoids, which all increase inflammation, capillary permeability, and vasodilation, as well as acting as an anticoagulant. Other cellular defenses include apoptosis initiating cells. NK, or natural killer cells, destroy unhealthy or unwanted cells. They form in the bone marrow, circulate in blood, and accumulate in secondary lymphoid structures. They perform immune surveillance in that they patrol the body and detect unhealthy cells. They destroy virus-infected cells, bacteria-infected cells, tumor cells, and the cells of transplanted tissue. They kill by releasing cytotoxic chemicals. This illustration shows a natural killer cell secreting cytotoxic chemicals such as perforin and granzyme. Perforin forms a transmembrane pore. Granzymes enter the pore, causing apoptosis of the cell, and the unhealthy or unwanted cell dies. Chemical defenses include interferons, which are a class of cytokines that are nonspecifically interfering with the spread of intracellular pathogens, for example, viruses and intracellular bacteria. Interferons alpha and beta are produced by leukocytes and virus-infected cells. They bind to neighboring cells and prevent their infection. They trigger synthesis of enzymes that destroy viral nucleic acids and inhibit the synthesis of viral proteins. They also stimulate natural killer cells to destroy virus-infected cells. IFN produced by the T lymphocytes and the natural killer cells will stimulate macrophages to destroy virus-infected cells. This illustration shows interferons. Step 1, the infected cell. And step 2, we have interferon alpha and beta. And then we've got 3A, synthesizes enzymes that interfere with viral replication. And then with 3B, it looks like perforin and granzymes. Also, there's a step 4 where a macrophage is going to phagocytize an infected cell. Another chemical defense is the complement system, which is a group of over 30 plasma proteins. They work along with a complement, or they complement antibodies. Complement activation follows pathogen entry. There's two pathways, classical pathway and alternative pathway. The classical pathway, the antibody attaches to a foreign substance, and then the complement binds to the antibody. In the alternative pathway, the complement binds to polysaccharides of bacterial or fungi cell wall. The complement system is especially potent against bacterial infections. This illustration shows a complement functions after the activation. So it increases inflammation. The complement increases inflammation through activation of various cells such as mast cells, basophils, neutrophils, and macrophages. The complement causes the elimination of immune complexes. The complement links with the antigen antibody complexes with erythrocytes, which are later stripped of these complexes by macrophages within the liver and the spleen. The complement activates opsonization, which serves as an opsin or a red flag by binding to a pathogen such as a bacteria, and this enhances phagocytosis of the pathogen by macrophage. And then cytolysis. Collectively, these complement proteins form a protein pore in a microbe's plasma membrane to cause cytolysis by an influx of fluid. Bye-bye bacteria. Okay, so inflammation is another chemical defense. It is triggered whenever body tissues are injured or infected. The 4 signs of inflammation are redness, heat, swelling, and pain. Inflammation prevents the spread of damaging agents, disposes of cell debris and pathogens, and sets the stage for repair. In step 1, leukocytosis occurs as neutrophils enter the blood from the bone marrow. In step 2, margination, where the neutrophils cling to the capillary wall. In step 3, diapedesis, the neutrophils will flatten and squeeze out of capillaries. And in 4, the chemotaxis, or the neutrophils will follow a chemical trail. And so as the neutrophils enter the area and the tissue fluid flows into the area and the blood vessels dilate, that causes the swelling, heat, redness, and pain. Fever is another chemical defense. It is the abnormal body temperature elevation and occurs when 1 degree Celsius or more from the normal 37 degrees Celsius body temperature. It results from the release of pyrogens from the immune cells or infectious agents. In the events of fever, the pyrogens circulate through the blood and target the hypothalamus. In response, the hypothalamus will release prostaglandin E2. The hypothalamus raises temperature set point, leading to fever. There are benefits of fever. Fever inhibits reproduction of bacteria and viruses. It promotes interferon activity, increases the activity of the adaptive immunity, accelerates tissue repair, and increases the cams on the endothelium of capillaries in the lymph nodes. Additional immune cells will then migrate out of the blood. It is recommended to leave a low fever untreated. There are categories of fever. A low grade is 100 to 101 degrees Fahrenheit. Intermediate grade is 102 degrees Fahrenheit. A high grade is 103 to 104 degrees Fahrenheit. And a dangerous high grade is over 104 degrees Fahrenheit. Seek a physician help if fever is intermediate or high grade, or if the low grade persists. There are risks of fever. There are changes in metabolic pathways and the denaturation of proteins, possible seizures, irreversible brain damage at greater than 106 degrees Fahrenheit, and death is likely if the temperature is greater than 108 degrees Fahrenheit. Now let's look at adaptive defenses. Adaptive immunity involves specific lymphocyte responses to an antigen. Contact with the antigen causes a lymphocyte proliferation. The immune response consists of lymphocytes and their products. Longer response time than the innate immunity. There are 2 branches of adaptive immunity: cell-mediated immunity involving T lymphocytes, and antibody-mediated immunity involving B lymphocytes, plasma cells, and antibodies. Lymphocyte activation. Lymphocytes originate in the bone marrow. Some travel to the thymus gland to mature. These are your T lymphocytes. Some stay in the bone marrow to mature. These are your B lymphocytes. Self-recognition is important so that lymphocytes do not attack normal body cells. They must be able to recognize a unique antigen and thus gain immunocompetence. Activating T or B cells produce effector lymphocytes and memory lymphocytes. Effector lymphocytes are short-lived and attack immediately. Memory lymphocytes will wait until the body encounters the antigen again, and it is the basis of adaptive immunity. It guards against subsequent infections. This shows lymphocyte activation. The pink is the site of lymphocyte origin, which will be in the red bone marrow. And the yellow is the site of the development of immunocompetence is B or T cells, which are the primary lymphoid organs, and then the green is the site of the antigen challenge, activation, and final differentiation of B and T cells. So in step 1, lymphocytes destined to become T cells migrate to the thymus and develop immunocompetence there. B cells develop immunocompetence in the red bone marrow. In step 2, after leaving the thymus or bone marrow as naive immunocompetent cells, lymphocytes establish themselves in the lymph nodes, spleen, and other lymphoid tissues where the antigen challenge occurs. In step 3, the antigen-activated immunocompetent lymphocytes circulate continuously in the bloodstream and lymph and throughout the lymphoid organs of the body. The primary adaptive response. Adaptive memory results from formation of a long-lived army of lymphocytes upon immune activation. Adaptive immunity activation requires contact between the lymphocyte and the antigen. There's a lag time between the first exposure and direct contact. Activation leads to the formation of many memory cells against a specific antigen. Generally, a person is very sick during their primary response if they're exposed directly to the pathogen. The secondary adaptive response occurs with subsequent antigen exposure. Many memory cells make contact with the antigen more rapidly, therefore they can take it out quicker, and this produces a powerful secondary response. The pathogen is typically eliminated before disease symptoms even develop. For example, a person who develops measles will not have it again, even if exposed. The virus eliminated by memory T and B lymphocytes and antibodies before causing harm. Vaccines are typically effective in developing memory, and some people do get a slight primary response when getting a vaccine. So this shows the primary response and how there's a lag phase. And so this generally gives the pathogen some time to take hold and disease usually occurs. Whereas in the secondary response, the memory cells are already present, and so the secondary response can occur much quicker before disease symptoms are usually even present. And if they are, then they're milder than they would have been in the primary response. So let's look at the cell-mediated responses and then the humoral responses. So for the cell-mediated responses, this involves the T cells. The targets are body cells infected by viruses or bacteria, abnormal or cancerous cells, and the cells of infused or transplanted foreign tissue. Antigen presentation occurs when cells display the antigen on a plasma membrane so that T cells can recognize it. There are two categories of cells presenting antigens: all nucleated cells of the body and the antigen presenting cells, or APCs. The immune cells that present to both helper T cells and cytotoxic T cells, and they include dendritic cells, macrophages, and B lymphocytes. This shows adaptive immunity, and you can see antigen presenting cells over here with the T cells. So effective against antigen within cells, and it requires an antigen presenting cell. T cells include a cytotoxic T lymphocyte and a helper T lymphocyte. And what they do is they destroy cells through apoptosis, kind of like a natural killer cell. The major types of T cells include CD8 cells and CD4 cells. CD8 cells are cytotoxic T cells, and they release the chemicals that destroy other cells through apoptosis. CD4 cells are helper T cells. They assist or help in cell-mediated, antibody-mediated, and innate immunity. For example, they activate natural killer cells and macrophages. There are other types of T cells, including regulatory T cells and memory T cells. This illustration shows the CD4 cell pathway to becoming the helper T cells and the CD8 pathway to becoming cytotoxic T cells. And we see that there are two different types of APCs, or antigen presenting cells. For the CD4 cells, looks like class 2 MHC protein is presented. And then for the CD8 T cell, the class 1 MHC protein is presented. The memory cells shown here in the center are what form that adaptive immunity that we've been talking about, that remembers the pathogen for the next time it might occur in the body. And then at the bottom here, the effector cells are the ones that are going to be the soldiers that actually go out there and fight directly. This is a summary of T lymphocyte function and how it binds to the target cell and secretes proteins that lyse the cell membranes and signals the cell to die. Then the T lymphocyte will detach and the target cell will die by apoptosis. Now let's look at the humoral response, which involves the B cells. So the targets here are bacteria and molecules in the extracellular environments. The cells of the humoral response are the B cells, which become plasma cells and secrete antibodies. Antibodies mark cells for the destruction by macrophages. This shows the primary response of a B cell, which is going to be the initial encounter with the antigen. We do not need an antigen presenting cell for a B cell. So the antigen will bind to the receptor on a specific B lymphocytes, and they will then proliferate to form a clone. And then after that, a plasma cell will form, which will secrete the antibody molecules. There will also be memory B cells, which are primed to respond to the same antigen. And then the secondary response, which it says can be years later, again, the memory cells are already there, and the subsequent challenge by the same antigen results in a more rapid response, and a clone of cells identical to the ancestral cells will occur, and a whole bunch of plasma cells will be proliferated that will secrete the antibody molecules, and then, of course, a staff of memory B cells will be proliferated as well, which will be stashed away for later future use if needed. So this is a summary of B lymphocyte function. The B lymphocyte will give rise to a plasma cell, which will secrete the antibodies. Antibodies then bind to antigens on the bacteria, marking the bacteria for destruction. And the bacteria-coated, or the antibody-coated bacteria are avidly phagocytized. It's, again, like a flag, kind of like opsonization, that signals the macrophage to come in and engulf that bacteria for dinner. So antibodies. They are immunoglobulin proteins produced against a particular antigen. Antibodies tag pathogens for the destruction by immune cells. They are good defense against viruses, bacteria, toxins, and yeast spores. Soluble antigens are combated by humoral immunity. Humoral means fluid. Their structure is Y-shaped soluble proteins. They are composed of 4 polypeptide chains, 2 identical heavy chains, and 2 identical light chains. The flexibility at the hinge region of the 2 heavy chains, and they are held together by disulfide bonds to form an antibody monomer. There are 2 important functional areas, the variable and constant regions. The variable region is what's going to actually bind to the antigen, and the constant region is the stem. And this shows the antibodies binding to different antigens. That's the variable region. Here's what the binding of the antibodies will do. In the first 3 on top, it says the binding of an antigen binding site of an antibody with an antigen causes neutralization, agglutination, or precipitation. Neutralization occurs when an antibody covers the biologically active portion of a microbe or a toxin, so it shuts down. Agglutination occurs when antibody cross-links cells forming a clump, and this can happen in your blood too with an improper blood transfusion. It can clump your blood cells together. Precipitation occurs when the antibody cross-links circulating particles, forming an insoluble antigen-antibody complex. And so they'll precipitate or solidify like out of the solution. And then the bottom three pictures show the exposed Fc or stem region following antigen binding by the antibody will promote complement fixation. So the Fc region of the antibody binds complement proteins and the complement is activated. Or it will promote opsonization. So the Fc region of the antibody binds to receptors of phagocytic cells, triggering phagocytosis. Or it will activate natural killer cells. So the Fc region of the antibody binds to a natural killer cell, triggering the release of cytotoxic chemicals like a T cell would do. Monoclonal antibodies are antibodies secreted by every plasma cell derived from the same B cell, and they all bind to only one antigen. They can be produced in vitro using myeloma cells. They're being used for quick and certain diagnosis of various conditions, for example, pregnancy tests, and they're used to carry radioactive isotopes or toxic drugs or tumors. To tumors. Finally, let's look at active versus passive immunity. Active immunity results from direct encounter with the pathogen. Passive immunity is obtained from another individual. So with active immunity, it can occur naturally by direct exposure to the antigen, or it can occur artificially through exposure from a vaccine. Memory cells against a specific antigen are formed. In passive immunity, it can occur naturally via transfer of antibodies from mother to fetus, like through the placenta or milk. It can occur artificially when serum transferred from one person to another, for example, antibodies to snake venom. So it could not even be just from one person to another, it could even be from an animal. And neither form of passive immunity produces memory cells. That's why it's passive. Active immunity occurs after the person is infected with a pathogen. So with the natural active immunity, there's actual exposure to the antigen. The primary response occurs and the person generally gets sick, and they make antibodies and memory cells. For artificial active immunity involving the use of vaccines, and this causes a primary response. Usually the vaccines are made of attenuated pathogens or their products, and so the person generally does not get sick. A second exposure will produce a faster and larger secondary response. The antibody titer is a test that's used to determine the amount of antibody in the plasma. And this shows the vaccine responses and how it will increase the antibody titer. So in passive immunity, a person is given prepared antibodies. It is temporary and no memory cells are formed. Natural passive immunity occurs when a mother passes antibodies to a child through the placenta or the mother's milk. Artificial passive immunity can be used in the event of an unexpected exposure to an infectious disease. The person is given a gamma globulin injection, like a serum that contains antibodies, the immunoglobulin proteins, G. So this sums up active and passive immunity. We can see in active immunity the production of memory cells due to the contact with antigen. Naturally acquired come from direct exposure to the antigen following entry of the pathogen into the body naturally. Artificially acquired is through a vaccine. For passive immunity, no production of memory cells. Antibodies from another person or an animal are introduced. Naturally acquired passive immunity comes from transfer from mother to child across the placenta or in the breast milk. Artificially acquired passive immunity comes from the transfer of the serum containing an antibody from another person or an animal. It's important to prevent the rejection of an organ transplant. It depends on the similarity of the tissues. The patient would be treated with immunosuppressive therapy, such as corticosteroid drugs to suppress inflammation, anti-proliferative drugs, and immunosuppressant drugs. And of course, since these are going to affect the immune system, many of these have severe side effects. Did you hear the joke about the germ? I'm not telling you. I don't want to spread it around. Thanks for listening.